Hello everyone, welcome to the Byjus exam prep, the most comprehensive app for all exams. Now we are going to discuss analog previous year questions from 2015, 2007 and 2001. That is conducted by IIT Kanpur. Okay, ready guys? It is a part 2. So first of all, let me know that sound quality, picture quality, everything is fine. Yes, please tell me sound quality, picture quality, everything is fine. Okay, I think now everything is fine. Now guys, in this session we will discuss important questions on Mosfet, BJT and combination of BJT and what diode, combination of BJT and what operational amplifier, right? And you can join my Telegram channel, that is Electronics by Sanjay Rathi. After the class, I will upload the PDF of this session on my Telegram channel, that is Electronics by Sanjay Rathi. Okay, so like the session, subscribe our channel and share the link of this session. Now we are going to start what? Analog part 2. And this session is important for electronics, electrical and instrumentation branch. And we will discuss questions from what? Electronics, electrical and instrumentation branch. Okay. This is my introduction. Myself Sanjay Rathi. I am having around 21 plus years of teaching experience in the field of competitive exams like EAC, GATE and PSU. I have qualified and selected for engineering services exam. These are my ranks: AIR 16 in EAC 2005 and AIR 21 in EAC 2008. And I have mentored more than 1 lakh students for these competitive exams, right? And according to my experience, for electrical branch, for electronics branch or for instrumentation branch, if you want to get the good rank, right, means what? Single digit rank or what? 2-digit rank, under 100 rank, then analog is going to play a crucial role in your selection. Remember that. And you will get the idea which type of questions we may expect in what? Right, incoming exam. Okay. Now this is for you. Get up to 90% scholarship on GATE preparation program on 20th August 8 PM. Please note the time, right, and go for this scholarship on GATE preparation program. Now my dear friends, first question on Mosfet in 2015 from electronics branch. Remember, the Mosfet is common for electronics, electrical and instrumentation. We may expect this type of question, direct formula based question. Everyone try to solve this question. A Mosfet in saturation has a drain current of 1 milliampere. Okay, 1 milliampere. For VDS is equal to 0.5 volt. 0.5 volt. If the channel length modulation coefficient is 0.05, channel length coefficient is represented by the lambda 0.05 per volt. What is the unit? Per volt. That is the volt inverse. The output resistance of the Mosfet. Output resistance, it is asked here. Now, what is the formula for everyone? Tell me, what is the answer for this question? Yes, please. What is the answer for this question? So, how many students are attending the session? Please like the session and simply use your notebook to solve this type of questions. Now, it is based on what? Early effect. Channel length modulation means early effect. And in case of BJT, it is known as what? Base width modulation, right? Or here in case of Mosfet, we are saying that channel length modulation, that is given by the early JM early. And the coefficient lambda is nothing but 1 by VA. 1 by VA. So what is the value of the ID? 1 milliampere at VDS is equal to 0.5. Then we have to solve this. To go through the characteristics of the Mosfet, now this is the characteristics. in saturation region, for example, that is the case, and this is the early effect. Okay, extend this line backside, and this is what VA. This is called early voltage. This is nothing but 1 by lambda. It is a negative value. Because it is a negative side, that one is what? Positive side. What is given here? Exactly at VDS is equal to 0.5 volt. What is the value of the current? 1 milliampere. This is given. On y-axis, it is the IDS. On x-axis, it is the VDS. And then you have to calculate what is the output resistance. So output resistance is nothing but slope of reciprocal of the slope of this line. This is called 1 by R0. Means you have to find the slope of this line and then you can find the R0. So very simple thing. Here it is a minus VA. So what is the slope? Slope is nothing but 1 by R0 is equal to Y2 minus Y1. Y2 minus Y1 upon X2 minus X1. This is the general formula. So 1 by R0. What is the Y2? This is the Y2, 1 milliampere. Minus, what is the Y1? That is the current is 0 here. What is the X2? 0.5. Minus of minus. What is the minus of minus? 1 by VA. What is the VA? Try to understand. VA is equal to 1 by lambda. I will give you the shortcut also. 0.05 means it will become 100 by 5. That is the 20 volt. That is nothing but 20 volt. You can put here minus of minus 20 volt. Now we can neglect, because this 0.5 is almost negligible as compared to 20. It is 40 times higher. We can neglect this 0.5. Then it will become 1 by R0 is nearly equal to 1 by 20. So what is the R0 is equal to? 20 kilo ohm. That is the answer. The answer for this question is 20 kilo ohm. Now, if you want the exact value, suppose if it is asked exact value of this, then you can directly find 1 upon 20.5. Get the value and find the reciprocal of that. Remember, the current is in milliampere, voltage in volt, and that's why it will be in kilo ohm. R0 will be in kilo ohm. This is called early effect. In the saturation region, the change in current because of the change in VDS, that effect is called what? Early effect or channel length modulation. In this way, we can find the answer. Second thing, very simple formula for this one. Directly you can find the R0 is equal to early voltage upon what? DC current. Or this is nothing but 1 by lambda IDS. So in some in some textbook, directly they will give you the solution 1 by lambda VDS. You can directly find 1 by 0.05 into 1. That is nothing but 20 kilo ohm. You can check. But this is the important thing, how to find the slopes. Sometimes they want exact value. This is the exact formula, how to calculate the output resistance. This is the first question on MOSFET. Students, in previous class already we have discussed question from what? Diode, circuits and operational amplifier, right? Go through that session. Part 1. Important numericals on what? Operational amplifier, and important questions from what? That diode circuit. Now, next question. Tell me, what is the answer? For the N MOSFET. N MOSFET means that is the symbol for the N MOSFET. VDD it is given. Now it is drain terminal. Drain terminal is sorted to what? Gate terminal. This is the source terminal. Now voltage at this point is VDD, because it is sorted means what? What is the gate voltage? VDD, and this is the VSS, this value. For the N MOSFET in the circuit shown, the threshold voltage is VTH. where VTH is greater than 0. Normally for N channel MOSFET, the VTH, that threshold voltage is positive. The source voltage VSS, this is the source voltage VSS, is varied from 0 to VDD. Is varied from 0 to VDD. Neglecting the channel length modulation. Neglecting the channel length modulation means what? Lambda tends to 0. Lambda tends to 0. The drain current ID as a function of VSS is represented by graphical answer. This is the first case, that is the second case, that is the fourth, and this is the third case ID. This is the C option. Which option is correct? Okay, give me the answer in comments box. What is the answer for this particular question? This is a simple previous year question. Yes, please. Now, very simple one. What is the answer? A or B or C or what? D. Very simple one. Now, I am giving you the hint. Everyone try to give me the answer. It is a 1 mark question. Try to understand. When the drain is sorted to gate, always remember, when the drain is sorted to gate, it means it is in saturation. Because VDS is equal to what? VGS. Because drain and gate voltages are same, VDS is equal to VGS, means VDS is greater than what? VGS minus VT. Right? It means it is in saturation. Okay, no problem. So in saturation, the current is given by half of K and S W by L VGS minus VT the whole square, where VT is the threshold voltage, VGS is the voltage between gate and source. Now, or you are giving the answer B. Okay, I will check. You are giving the answer B. My dear, what is the scale here? It is VSS. It is VSS here. It is not VGS. It is the VSS. Right? The drain current ID is a function of VSS. Now, try to understand what is this? The voltage at this point, this is the source terminal voltage. It is nothing but VSS. This is applied voltage. It is a variable. Voltage at this point is nothing but VDD. Tell me, what is the VGS? VGS is nothing but VG minus VS. So what is the VG? Fixed value VDD minus VSS. To put this value here, you are going to get the half of K and S. W by L, this is constant, and this will become VDD minus VSS minus VT whole square. So everyone tell me, exactly at 0, when the VSS is 0, we are getting the maximum current. Or when we are increasing the VSS, what about the current? Current decreases. And what is the relation? Square of that. So when the VSS is 0, ID is maximum. Or when we are increasing the VSS, ID will decrease. And finally it will become 0. Right? When it will become 0. Okay. Now, which answer, which will satisfy the condition? This one. No doubt. This is not the correct one. This is not the correct one, because it is an increasing function of VSS. This is decreasing, that is decreasing. But it is a linearly decreasing. That is the just direct inversely proportional to that. But it is the case. This is the right answer for this particular question. A is the correct one. A is the correct one. Nivedita, now it is clear to you, everyone. The answer for this question is what? A. So this is a very simple conceptual question from the MOSFET. Directly 1 mark question. Always remember, when drain is sorted to gate, it will be in saturation region. This is in saturation region. And for this formula is valid for saturation region. Okay. Now, next one. Now, another question in analog. Again, a very simple one. In the AC equivalent circuit in 2015, set 2 of electronics, we will solve the question from electrical branch also. Don't worry. So in electrical, we are having very easy question as well as very conceptual question. Both type of question in electrical branch and in what? Instrumentation branch. First of all electronics, then electrical, then what? Instrumentation from the transistor and MOSFET. In AC equivalent circuit, the two BJT are biased in active region. Let this BJT is in active region. This is the PNP. This is NPN. Right. Have the identical parameters with beta very greater than 1. Beta is very large as compared to what? 1 comparison to 1. And that's why we can neglect the base current. Base current is 0. The open circuit small signal voltage gain is approximately. Open circuit small signal voltage gain is approximately. What is the answer? Okay. Now, if it is asked, for example, normally students, in AC equivalent circuit, this is already equivalent circuit, nothing is given, right? What about the sources here? This sources is 0. We are taking all the DC sources 0. This sources is 0. Means when we are making all the DC sources 0, it is nothing but AC equivalent circuit. Okay, no problem. Now try to understand what is the base current, my dear students. The base current is 0. But when it is asked small signal voltage gain, the number of students, first of all, they will try to draw what? Equivalent circuit, small signal model. The small signal model, no need to draw the small signal model. We can use a very simple concept. Right, try to understand. If the beta is very large, so what is the base current? What is the base current in first transistor and what is the base current in the second transistor? 0. For a small signal, again it is 0. IB1, IB2, it is 0. So what about this current? Emitter current enter into this, collector current leaving this, collector current entering into this, emitter current leaving this, all are equal. They are connected in series. When they are connected in series, the currents are equal. If the currents are equal, emitter current is equal for this transistor and that transistor, so what about this voltage? The small signal voltage VB for second transistor for NPN is equal to what? The voltage at this point. VEB. Because in case of PNP transistor, we are using the VEB. Right? So VEB and VBE are equal. The equal magnitude. They have the same value. For PNP transistor, it is positive. For NPN transistor, VEB is positive. VBE 2. Right? Why they are equal? Because the currents are same. They are connected in series. Now, my dear friend, write down the KVL from this point to this point. When I am writing the KVL, this is the plus, this is the minus, you will get the V out. What is the V out? V out is nothing but minus of VEB. Yes, you can check. Write down the KVL. You will get the V out is equal to minus of VEB1. And what is the V in? VBE2. VBE. This is for NPN. This is for PNP. So what is the V out by V in? That is called gain. Both are equal and that's why you are going to get the minus 1. What is the answer? Minus 1. Is there any need to draw? Is there any need to? This is not Rakesh sir. This lecture is recorded. No. It is a live session. Rakesh, I'm right. Just it is a live session. Okay. Try to give the answer. Answer in comments box. Now VEB1 and this is the VBE2. Now remember, we can also draw the small signal model, but no need to draw. In every case, no need to draw the small signal model. We have the idea about the small signal model, RE model. Very simple. What is the RE model? Right? Like this. This is the RE. This is called alpha I. And this is the base. This terminal is called emitter terminal. This terminal is called collector terminal. You can connect this to find a small signal model, and again you are going to get the same answer, -1. Now remember, the base current is negligible, and that's why the IC is equal to what? Alpha I, and IC is equal to IE. So alpha will become 1. When the beta is very, very large, always remember alpha will become 1. And then use this model, connect accordingly. But in this particular question, no need to apply the small signal model because they have the same current. Similar question in MOSFET. Similar question, right? The answer is -1. Now, what is the answer for this one? Take your time and give me the answer. यार एक बार जरा लाइक, सब्सक्राइब और शेयर कर लीजिए इसे. Ask your friends to join the session so that we will get right answer. What is the answer for this question, everyone? In the circuit shown in the figure, the BJT has a current gain of 50 beta. For an emitter base voltage VEB, again this is a PNP transistor. In 2015, one question on PNP transistor in set 2, again in set 3, again one question on what? PNP transistor. So in PNP transistor, this is called VEB, right? This is called VEB. What is the value of the VEB? 600 millivolt. 600 millivolt means nothing but 0.6 volt. In PNP transistor, we have to apply the VEB, and NPN transistor, we have to apply the VBE. The emitter collector voltage VEC. This is the, we have to find the VEC. Plus, minus, this is the collector terminal. This is the emitter terminal. The voltage between this emitter and collector is called VEC, and this is the VEB. Okay, no issue. So what information is given here? Right, very, very simple information that in the circuit shown in the figure, BJT has a current gain beta of the 50. For an emitter base voltage 0.6, the emitter collector voltage is. If this voltage, we have the idea about this voltage, right? Now we can calculate the base current. Always remember the direction of the base current is like this, outside the circuit, outside. What is the direction of the collector current? Outside the transistor. What is the direction of the emitter current? Inside. This is the actual direction of the base current and collector current. Then we can find the IB. I am writing the KVL. Let this is the IB. This is the VEB. Okay. Now, from this point to this point, write a KVL. You will get 3 is equal to VEB plus 60 times of IB. What is the value of the IB? 3 minus VEB upon 60. 3 minus 0.6 upon 60. Right? You can calculate 2.4 upon 60 milliampere. Why milliampere? Because resistor is in kilo ohm, that is in volt. Right? So this is the value of IB. Okay. Okay. Okay, I will give the answer for that question. Wait for 2 minutes, Suresh. Okay. I have some concept, 1 or 2 subjects a week. Now, try to solve what number of questions. Already you have covered the syllabus. Then now concept with what? Numericals. Go for concept with numericals. Automatically you will get the idea. Which portions are weak and which portions are strong. Now, IB, first of all find IB. Then, what is the value of the IC? In active region, IC is given by beta IB. What is the beta? 50. So 50 times of into 2.4 upon 60. So this is the value of the IC. You can find the value of the IC. Now what is the value of the VEC? VEC. My dear friend, VEC is nothing but VE minus VC. What is the VE? VE is nothing but 3 volt. Voltage at this point is called VE. This is the 3 volt. minus, what is the VC? IC into 500 ohm. Always convert it into kilo ohm, 0.5 kilo ohm. Resistor should be in kilo ohm, current in milliampere and voltage in volt. So IC into 0.5. IC into 0.5. Use this IC here and you will get the answer for this particular question. What is the answer? Yes, please. Right. So that is how to solve the PNP question based on what? PNP transistor. That is a very simple way. This is the VEB. Write down the KVL, get the value of the IB, multiply it with what? Beta, right? And get the value of IC. Once you have the value of the IC, get the value of the voltage at this terminal. This is called VC. What is the VC? IC into 0.5. What is the VE? 3 minus 0.5 into IC will give you the value of VEC. That is the answer. That is the answer for this particular question. Okay. Now next one. Okay. तो अरे आंसर तो दे दो कैलकुलेशन करके, क्या है आंसर? What is the answer for this question? Okay. Again, formula based question. Next one. It is in electrical branch in 2015. 1 mark question in electrical branch. When a bipolar junction transistor is operating in the saturation mode, right? Simple saturation mode. Which one of the following statement is true about the state of its collector base and base emitter junction? Right. Please tell me what is the answer for this question. Very, very easy question. For saturation mode, everyone give me the answer in comments box. For saturation mode, this is emitter terminal, this is base terminal, and this is collector terminal. This junction is called collector junction, this junction is called emitter junction. For saturation reason, what about the collector base junction and what about the emitter base junction? This is called collector base junction, CBJ. Or this is called emitter base junction, EBJ. Okay. And in saturation, both the junctions should be, acha, current. What is the answer for that previous question? 2 volt. Okay. Yes, you can solve this question. Yes. 0.4, 5 into 0.4, it is nothing but 2 milliampere. When the 2 milliampere is multiplied with the 0.5, it will become 3 minus 2 into 0.5. Yes, you are getting the 2 volt. That is the answer for this question, 2 volt. Yes. This is the 2 volt. Now, which answer is correct? Here it's very simple. We are having the 4 modes. Normal active mode, reverse active mode, cutoff, and what? Saturation. So it is a saturation. In a saturation, both the collector and emitter base junction are forward biased. Right. When the collector base junction is forward biased and base emitter junction is reverse biased, everyone tell me which mode? A is which mode? So we can say A is what? Reverse active mode. Reverse active mode or inverse active mode. What about the B? Collector base junction is reverse bias and base emitter junction is forward bias. Base emitter junction is forward bias, normal active mode. Or simply we are saying that active mode. Normal active or forward active mode. Answer for our question, saturation. Both the junction reverse bias, cutoff mode. This is the cutoff mode. Okay, very simple. Right, C is the answer for this question. Very easy. Now, another question in 2015 from the electrical branch. Now, in the given circuit, a silicon transistor has beta is equal to 75 and a collector voltage VC is equal to 9 volt. In the given circuit, the silicon transistor has the beta is equal to 75 and the collector voltage VC is equal to 9 volt. Then the ratio of RB and RC. RB and RC, you have to find the ratio of RB and RC. base resistor upon collector resistor. It is connected to collector terminal, it is connected to base terminal. The voltage at this point, because it is given the silicon transistor, and that's why we are taking at 0.7 volt. It is not mentioned, but we can, typical value is 0.7 volt. Beta is 75. You have to calculate VC. VC is given as 9 volt. Beta is given as 75 volt. Now, normally, current distribution. What is the Jaya, Priya? Yes, active current. Yes, please try to give me the answer for this question. VC in electrical set 1 in 2015, 2 marks question. Right. Now watch this. This is the base current IB. This is the, always distribute current like this. This is the collector current IC. This is the base current IB. When the collector terminal is connected to what? Base, through a resistor or through a short circuit, always remember, when the collector is connected to the base, then it is always in active region. This is the active region. From this point to this point, if it is connected, then always it is in active region. When it is in active region, no need to verify. Directly we can say it is in active region. And high voltage is applied here. Now, what is the base current? Here, the current is collected, IC here, IB. So, what is the current here? IC plus IB. Now, in active region, IC is equal to beta IB. That is nothing but 75 times of IB. What is the I is IC plus IB? IC plus IB is equal to beta IB plus IB. Beta plus 1 times of IB means what is this? 76 times of IB. Now we are having, this is a 9 volt. Okay. It is a 0.7 volt. Now my dear friend, what is the drop across this RC? When I am calculating the drop across this RC is very simple. 15 minus 9, that is what? 6 volt. Very simple. 15 minus 9, what is the drop across this RC? 6 volt. What is the drop across this RB? 9 minus 0.7 volt. 9 minus 0.7, I can say directly 8.1 volt. 8.3 volt. It is visible. 9 minus what? 0.7. 9 minus 0.7 is what? 8.3 volt. This is the drop across this RB. Right. Now, drop across RC or drop across RB. We can say, what is the current through this? 1 plus beta times of IB into what? RC. Oh, sorry. First of all, I am writing the RB. IB into what? RB. Upon. What is the current through this? 1 plus beta times of IB into what? RC. You have to calculate the ratio of RB and RC. So my dear students, IB cancel. Tell me, this is given as, what is the drop here? We have the value 8.3. What is the drop here? 6 is equal to RB upon 51 times of RC. What is the answer? You can calculate. into 8.3 upon 51 into 8.3 upon 6. What is the answer? Yes, please. What is the answer for this question? 1 minute. Okay, easy guys. Means simply distribution of the current. Some students are making the silly mistakes. They are neglecting the IB. this current is what? IC plus IB in this branch, and that is the way. Find the drop across the resistor, find the drop across the resistor, find the current through the resistor, and simply get the ratio. Check my calculation and you will get the right answer for this question. Okay. So next question. Normally the RB is very high as compared to what? RC. Right? Normally. Yes. Okay. I think that is clear to you. It is in electrical branch in 2015. Now, next question. Similar type of question in electrical branch in set 2 2015. This time, in the following circuit, the transistor is in active mode. It is given it is in active mode. VC it is given as 2 volt. To get the VC is equal to 4 volt. Initially it is the 2 volt. Now we want the 4 volt. We replace RC with the RC dash. It is replaced by RC dash. Then the ratio of RC dash by RC. Everyone tell me, it will be less than 1 or greater than 1? Less than 1 or greater than 1. Very simple. Very simply we want. Initially it was what? 2 volt. Now we want it should be what? 4 volt. Means VC increases. When VC increases, what should be the RC? What should be the RC? It should be decreases or it should be increases? Now, I'm going to solve this question. Very simple. Now, when this is the IC, this is IB, it is in active mode, it is given in the question. This is 0.7 volt. My dear friends, I am not changing the value of RB, I am not changing the value of 10 volt, I am not changing the value of this VB, means IB will remain constant. IB is equal to 10 minus 0.7 upon RB. It will remain constant. If it will remain constant, what about the IC beta IB? Because it is in active region, it will also remain constant. No variation. No variation in IC. Now, yes, less value is required. Now, how to calculate the value? So, what is the value of the VC? In first case, VC1 is given by 10 minus IC into RC. 10 minus IC into RC. And that is given as 2 volt. 10 minus IC into RC. So what is the IC-RC? IC-RC will become 8. That is the first case. In second case, VC2 is nothing but 10 minus IC into RC dash. And what is the VC2 given in the second case? 4 volt. This is the 4 volt. Now, what is the IC-RC dash? IC-RC dash, it will become 6. Now, this is the equation number 1. This is the equation number 2. Ratio RC dash by RC is required, 2 divided by 1. 2 divided by 1. RC dash by RC, it will become RC dash by RC 6 by 8. That is nothing but 3 by 4, 0.75. 0.75 is the answer for this question. Right? Directly, simple, it is given in the question. Or always remember, if this VCE, initially it is given as 2 volt, then 4 volt, means it is greater than what? VCE set. What is the VCE set? 0.2 volt. For silicon. If it is greater than 0.2 volt, means definitely this transistor is in active region. But no need to verify because already it is given in the question. It is given in the question. That was the nature of the question in 2015. Okay. Again, that is based on the ratio. That is based on the ratio. Okay. Now, simple calculation. Some students, what they will calculate, they will try to calculate the value of the IB. Sir, RB is not given. How to calculate the IB? But when we are calculating the ratio, always remember unknown. If suppose that RB is unknown, simply cancel out. Right? No need to calculate the IB. And always remember in active region, IC is equal to what? Beta IB. Next question. Next one. Now the question from instrumentation branch. If you are from electronics branch, then try to solve the question from electronics, electrical and instrumentation. If you are from electrical branch, again electronics and instrumentation with what electrical. And if you are from instrumentation branch, already you have solved this question, then give me the answer. And electronics and electrical student, give the answer for this question. Give me the answer for this question in comments box. And after the session, just at the end of the session, I will give you some assignments. Try to give me the answer in comments box or on my Telegram channel, that is Electronics by Sanjay Rathi. And in next class, I will mention your name also. Okay, in class, I will mention your name. I will upload your solution also. Okay, on the slides. Okay. Tell me, and you have that I am sharing my Telegram channel link. Please join that channel, Electronics by Sanjay Rathi. Okay then. What is the answer? In the circuit shown in the figure, it is found that VBE is equal to 0.7 volt. VE is 0 volt. This VE is given as 0 volt. Beta DC is 99 for the transistor. Then the value of RB in the kilo ohm. What will be the value of the RB? Okay, bhai. That is a question from instrumentation branch in 2015. Okay. Then how to solve this type of questions? First of all, give me the answer. What is the answer for this question? This voltage is given as 0.7 volt. This voltage is given as 0.7 volt. Beta DC is 99. Then the value of RB in kilo ohm is, value of RB in kilo ohm, that is, this is the RB in what? Kilo ohm, 10, this is the IB. This is the IC. And this is what? IC plus IB. This is plus IC plus IB. What is the IC plus IB? This is nothing but IE. Now, if it is 0 volt, or always remember, IE is equal to IC plus IB, means we can write beta IB plus IB. This is nothing but beta plus 1 times of IB. Very easy. If you want to calculate the value of this resistor, you have to calculate the IB. Why? You have to calculate the voltage at this point, that is 10 volt. What is the voltage at this point? Like this is the VB. Now what is the value of IB? If we have the idea, then we can calculate the RB. What is the RB? Voltage at this point 10 volt minus voltage as the base terminal upon the current, base current. That is the formula. Now, to calculate the IB, first of all calculate the IE. What is the voltage at this point? 0. What is the voltage at this point? Minus 10 volt. This is called minus VEE. Minus 10 volt. So 0 minus of minus 10 volt upon 1 kilo ohm. IE is given by 0 minus of minus 10 volt upon 1 kilo ohm. That is the 10 milliampere. This is the value of IE. 0 minus of minus 10, 1 kilo ohm. Okay. IE. So what is the IB? IE upon 1 plus beta. 10 milliampere divided by, what is the value of the beta? 99. So 1 plus 99, that is nothing but 100, and that's why the base current will become 0.1 milliampere. 0.1 milliampere is the base current. So you are giving the 93 kilo ohm, Vipul Viswas. Okay, I will check. Now we are getting the IB. Now what is the value of VB? My dear friend, the drop from this point to this point is what? VB. The value of the VB in the question is given as 0.7 volt. So what is the VBE? VBE is nothing but VB minus VE. Now this is given as 0.7. This is the VB minus. What is the VE? VE is 0 volt. That's why what is the value of VBE? 0.7 volt. Now we have 10.7 IB. So what is the value of the RB? 10 minus 0.7 upon 0.1. 9.3 upon 0.1, 93 kilo ohm. Right answer. 93 kilo ohm is the right answer. People, your answer is correct. Right? So this is a very simple question from the instrumentation branch. But important question. Same question we may expect in what electrical or what electronics branch. Right? So this is the very simple way. Always remember, some students are confused. What is the meaning of the VB and what is the meaning of the VB? My dear, VB means the voltage between the two terminal, base and emitter. And VB means the voltage of the base terminal with respect to ground. With respect to what? Ground. This is the VB. And VB means between base and emitter. No doubt emitter is 0. That's why the VB and VBE are same. VBR, otherwise you have to calculate the value. You have to calculate the value. Please try to avoid the silly mistakes, and that is the answer, 93 kilo ohm. Now, next one. Now in what? Instrumentation branch question from what? Mosfet. This 30 volt is given, this connection. NMOS. This is also NMOS, both are NMOS. Very simple and conceptual question, 1 mark question. 30 volt NMOS, V out, 10 volt is connected here. What is the output voltage? In the circuit shown in the figure, both NMOS transistors are identical, means all the characteristics are same. With their threshold voltage being 5 volt, VT is given as 5 volt. Ignoring the channel length modulation means lambda is equal to 0. The output voltage V out in volt is, output voltage V out in volt is, what will be the output voltage? What is the answer? Give me the answer. What is the answer for this question? Now, watch this. Now, my dear friends, these two are connected in what? Series. When these two transistor or MOSFET are connected in series, similar question, already we have solved one question. Two transistors are connected. The current, let this is the ID1, let this is the MOSFET number 1. Same current here, ID1. Same current here, ID1. Same current here, ID1. Why? Because the gate current is 0. Gate current is 0. When the currents are same, what about the value of the VGS? VGS will also be same for both the transistors. Since ID1 is equal to ID2, and therefore VGS1 is equal to what? VGS2. Now, this gate drain terminal of the first is connected to the gate terminal of the first. When the drain and gate are sorted, this is in saturation. Since both have the same characteristics, that's why it is also in saturation. Both are in saturation, no issue. Both are in saturation. Now, for this NMOS, what is the VGS2? So when I am calculating the NMOS for the second transistor, this is the 10 volt. So what is the VGS2? Nothing but 10 volt. So what is the VGS1? It is also 10 volt. The voltage at this point is 10 volt. Voltage at this point is 30 volt. So what is the output voltage? 30 minus 10. What is the output voltage? 20 volt. 30 minus 10, the output voltage is 20 volt. Very simple. Right? I think that concept is clear, everyone. So always remember, when NMOS or identical NMOS are connected in what series, the current will remain same. If the current will remain same, means both are identical, and that's why VGS and VGS2 are same. When VGS2 are same, that is the 10 volt. 30 minus 10, you are going to get the value 20 volt. 20 volt is the answer for this question. 20 volt in 2015. Next one. Oh, this is a very simple one in electronics 2007. Again, that is the paper conducted by what? IIT Kanpur. So please give me the answer. That is the previous year question series. Right? That is IIT Kanpur. And we are discussing the 2015, 2007 and 2001 question from these 3 years. And tomorrow at 9 p.m. Signal and System by Rakesh Talreja sir. Okay, so subscribe our channel, share the link of this session, right, and like the session. Tomorrow onwards, questions from Signal and System. Everyone please join that session. Okay. Now your answer is correct, 20. Now what is the answer for this question? In a transconductance amplifier, it is desirable to have. Now we are having the 4 types of amplifier: voltage amplifier, current amplifier, transconductance amplifier and transresistance amplifier. So which answer is correct? It is a transconductance amplifier. Okay. Now my dear, transconductance. Always remember, transconductance means what is given. Remember, transconductance means GM. GM means at this point we are applying the voltage, and at this point we are getting the current. Right? This is the transconductance. Voltage is converted into current. When I am giving the equivalent circuit, always remember, when equivalent circuit, always the input side is represented by its input resistance, and output side it is represented by a current source. Why? Norton's equivalent. This is a dependent source. The value of this is given by GM into VI. VI is nothing but voltage across this RI. This is called input resistance of the amplifier. This is the VI. Now here we are connecting what? A voltage source. Everyone try to understand. This is the voltage source. And the RS is its internal resistance. And the VI across the RI will convert it into a current. And then this is the output resistance. R0. Here we are connecting the RL. Actually load is connected here. So green one is the outside and that white portion is what? Equivalent circuit of the amplifier. Now, we want it will convert this VI into what? Current. We want the complete voltage should come across what? RI. What is the RI ideally? It should be infinite. Or practically it should be very greater than what RS. If it is the case, then what is the II? II is almost 0 and VI is exactly equal to what? VS. Right? So that is the case. Second, what about the current? We want that complete current should pass through what? RL. If the complete current should pass through the RL, then what about the R0? It is amplified current. It should pass through the RL. So R0 ideally it should be infinite. So that the complete current will pass through the RL, or R0 should be very greater than what? RL. Very greater than RL. And that is the condition. Which answer is correct? Large input resistance and large output resistance. A is the correct one. Right? So A, kaun diya? Balakrishnan. Yes, Balakrishnan, your answer is correct. Your current, check your answer. That I think that explanation is clear to you, everyone. This explanation is clear to you. Right. Now, my dear friends, we have the 4 types of amplifier: voltage amplifier, current amplifier, transconductance and transresistance. Everyone please draw the equivalent circuit of these amplifiers and verify it. Right? Right. So always draw the equivalent circuit for voltage source, for current source. When there is a current, draw the Norton's equivalent. When there is a voltage, draw the Thevenin's equivalent. Okay then. No problem. Please check this. Ideal value, practical value. No. This is a question in GATE EC 2007. For the BJT circuit shown, assume that the beta of the transistor is very large and VB is 0.7 volt. VB, this is the 0.7. And the mode of the operation of the BJT is cutoff, saturation, normal active, reverse active. There are 4 modes: cutoff, saturation, normal active, reverse active. Check the transistor and give me answer that particular transistor is in which mode of operation. Yes, please. Now, in this case, what is the beta? Beta is very, very, very large. When the beta is very large, so what is the base current? 0. Beta is not given, then how we are going to calculate? Beta is very, very large as compared to 1. Then always we are considering the base current is equal to what? 0. Now the emitter current and collector currents are equal. I. Then how we can check whether it is in cutoff or saturation and so on? No, it is not in cutoff. Why? Because when the 2 volt is connected, it is greater than what? 0.7 volt. Means it is not in cutoff. That junction is what? Forward bias. But according to 10 volt battery, it is visible that it is a reverse bias. So directly now some number of students will give the answer, sir, it is in normal active mode. Okay. But you have to check. How we are going to check this transistor? Very simple. First of all, let this is the 0.7 volt. And IE. Directly apply the KVL here and find the value of the IE. When I am going to find the value of the IE, this will become, write down the KVL, minus 2 plus 0.7. This is, I am writing the KVL, minus 2 plus 0.7 plus 1 into IE is equal to 0. So what is the IE is equal to? 2 minus 0.7 upon 1. It is 1.3 milliampere. Okay, when I am solving, directly when I am solving this will give you the answer that, okay, 1.3 milliampere, that is in active region, okay. But when we are solving this, that is the current for active region. But actually, when I am calculating the IC set, let this is the 0.2 volt. What is the lowest voltage at this point? 0.2 volt. Same current IC, same current IE. Now write down the second one. First of all, calculate from the KVL. Now write down the KVL in outer loop with taking VCE is equal to what? 0.2 volt. That is the method. Take the VCE is equal to what? 0.2 volt, because it is given, right? Transistor large, VB 0.7 volt, means it is a silicon transistor. We can assume that, let this is the saturation voltage. Write down the KVL in the outer loop. Minus 10 plus 10 times of IC plus, this is nothing but VCE set 0.2 volt, plus again I is equal to IC. We can write IC into 1 kilo ohm is equal to 0. Everyone calculate the IC here. IC will become 10 minus 0.2 divided by what? 10 plus 1, 11. That is nothing but 9.8 divided by what? 11. Okay. This IC is nothing but IC set. This IC is nothing but what? IC set. It is the maximum current. It is the maximum current. Now calculate this current. When I am going to calculate this current, no need to calculate. 9.8 divided by 11, it is less than what? Less than 1. Or what is the current in active region? Greater than 1.3 milliampere, means what? IE active, or this is nothing but IC active, is greater than what? IC saturation. Not possible. Not possible. So definitely it is in which mode? Saturation mode. Yes, Jaya, your answer is correct. Your answer is correct. It is in saturation mode. To find this value, then find this value and compare these two. Normally, actually we are having the idea that what if the beta is given, we are going to calculate the IB. What is the IB minimum? IC set upon beta. Then we are calculating the IB. And IB, it should be less than IB minimum for active region. or IB should be greater than or equal to IB minimum for saturation. This is for saturation and this is for what? Active region. But in this case, beta is not given. Beta is very large, so we can't calculate the IB minimum. If we are not able to find the IB minimum, then you have to use this concept. Okay, I think now it is clear to you. Next question, next is okay, that is on what Zener diode, and then with this question I will explain what is the role of this circuit, what is the role of the transistor. Okay, tell me, what is the answer for this one? Right. Tell me, what is the answer for this one? For the Zener diode shown in the figure, that is a question in electronics branch in 2007. Right. For the Zener diode shown in the figure, the Zener voltage at knee is 7 volt. The knee current is negligible and the Zener dynamic resistance is 10 ohm. If the input voltage range is from 10 to 16 volt, the output voltage range from. Normally, when we are assuming that Zener voltage at knee is 7 volt, means its breakdown voltage is 7 volt. Right? It is a practical Zener diode. So once it is in breakdown, the voltage will be constant. But here, the range of the output is given. In this question, we are using the practical Zener diode with its dynamic resistance. So what is the range? Option A, option B, option C, or option D. Now, if you want to solve this question, remember characteristics of the Zener diode. What is the characteristics of the Zener diode? First of all, Zener diode works in reverse direction, means when it is reverse bias. Our actual characteristics is like this. Somewhat elevated, just I am zooming it, that is the elevated curve. This is called knee voltage and that is called knee current, IZK. VZK. And what is the dynamic resistance of this? 1 by, this is the slope of this line is what? 1 by RZ. What is the value of RZ is given? 10 ohm. 10 ohm. If that is the characteristics, always remember, if this is the characteristics of Zener diode, so when the Zener diode is reverse bias or it is in breakdown region, it should be replaced by what? Its knee voltage VZK and in series dynamic resistance RZ. That is a simple case. Now, what is the value of the VI? 10 to 16 volt. That is greater than its knee voltage. What is the knee voltage? Only 7 volt. That's why definitely this diode is in what? Breakdown region. Right? Why? Because the applied voltage is 10 to 16 and it is greater than the 7 volt. What is the 7 volt? Its knee voltage. So it is in breakdown region. So if it is in breakdown region, simply you can replace the Zener diode by its equivalent circuit. What is its equivalent circuit? This is replaced by (7 volt) its knee voltage, and what is the RZ? 10 ohm. And what is the voltage at this point? 200 ohm. And this is the variable from 10 to 16 volt. Now you can find the value of V0. You can find the value of V0 by using the concept of what? Network. Very simple. Now it is a question from the network. Now you are going to find the V0 is equal to Vi into 10. This is always, remember, voltage division rule. Vi into 10 divided by 200 plus 10, 210, plus 7 into 200 divided by 210. Okay. Now this is cancel out. This is become Vi by 21 plus 20 by 3. Now put the two values of Vi. So what is the V0 one? 10 divided by 21 plus 20 by 3. And what is the second one V0 2? 16 divided by 21 plus 20 by 3. And you will get the answer. What is the variation? This is the question on practical Zener diode. And the answer, I think this is the 7.14 to 7.43. Now, one student may ask, sir, what is the use of the Zener diode? I have learned that what is the variation across the Zener diode? It should be 0. The voltage across the Zener diode should be constant. But practically there will be the variation because of its dynamic resistance. Right? And remember, what is the variation in the input? Variation in the input is 16 minus 10, 6 volt variation. And what is the variation in the output? 7.43 minus 7.14. Okay, this is a very less variation. This is a very less as compared to what variation in the input voltage. There will be the slight variation in the output. Now this time we have the MSQ. We can expect this type of question in MSQ, multiple select questions. Okay. Yes. Okay. So that is the question. Yes, Pankaj. For voltage regulation, but practically very high variation in the input, very low variation in the output. Okay. And Zener diode should be in breakdown region. Remember that. Now, that is the question. Now, last one. The 3-terminal device linear voltage regulator is connected to a 10 ohm load resistor as shown in the figure. 1 kilo ohm, 10 ohm load resistor. This is the 10 ohm load resistor. What is the power dissipated in the transistor? Now, in this question, if you want to calculate the power dissipation, always remember, this is the 10 ohm resistor. We are calculating the output at this point. Here the current is emitter current. Here the current is collector current. In the question, beta is given. If remember, if the beta is not given, what is the base current? Base current is negligible. If the beta is given, then we have to consider the current. But if the beta is not given, you can neglect the base current. Okay, no issue. Now, what is the power dissipation across the transistor? You have to calculate the value of VCE. VCE. So the voltage at this point is fixed 10 volt. What is the voltage at this point? Always remember, transistors should be in active region and Zener diode should be in breakdown region. That is the condition applied for this type of voltage regulator. Give me the name in the comments box, everyone. It is a series voltage regulator or shunt voltage regulator? Series voltage regulator or shunt voltage regulator? I will mention your name in the next class. Okay, please. Now, this is the load RL. This is the VB 0.7. Then we can calculate the output voltage. What is the regulated voltage, output voltage? That is given by VZ minus VB. What is the VZ? 6.6 minus VB. VB is given in the question? Not given. You can take the 0.7 volt. When we are taking the 0.7 volt, you will get the 5.9 volt. Check my calculation. This is the value of V0. Now the voltage at this point is 5.9 volt. Voltage at this point is 10 volt. So what is the value of the VCE? You can calculate the value of VCE is equal to 10 minus 5.9. I think it is 4.1 volt. 4.1 volt is the value of VCE. Now, second thing, 4.1 volt. What is the current here? I and IC are equal. So what is the I? I is nothing but V0 by 10. So what is the IC is equal to I, nearly equal to, because base current is negligible. It will become V0 upon RL. What is the V0 here? V0 is the 5.9 divided by what? 10. 0.59 ampere. Now you can calculate the power dissipation PT, VCE into what? IC. This is the formula. VCE into IC, it will give you the power dissipation across the transistor. That is the value. So everyone, what is the answer for this question? Nearly equal to 4.1 into what? 0.59. 4.1 into 59. Give me the answer fast. $2.419 watt. 2.419 watt means nearly equal to, B is the answer, 2.4. To always remember, and now my dear friend, what is the series and shunt? It is a series voltage regulator. Series means this transistor is connected in series with the RL. This is the series connection, and that's why it is called series voltage regulator. In shunt voltage regulator, transistor is connected parallel to the RL, like this. Like this. This is the parallel connection, and that is called what? Parallel. Shunt voltage regulator, series voltage regulator and shunt. Now in MSQ, my dear, in MSQ they may ask what is the name of this voltage regulator and what about the transistor. It is in a common emitter, common collector or common base configuration. In comments box, everyone give me the answer. In next class I will mention your name. What about the transistor? It is in which mode? In this particular circuit it is in which mode? Common emitter, common collector or common base. There are three options: common emitter, common collector or common base. Now time for assignment. Everyone, this is a very important question in electrical branch in 2007. That is the first assignment. Very important question. If you want the answer for this type of questions with complete explanation, join my Telegram channel, that is Electronics by Sanjay Rathi, and give me the answer in comments box. Right. No, not common current Gupta. It is not in common emitter configuration. Remember that. In this case, right, watch this carefully. Where we are taking the output, where we are giving the input. This is the input. So what is the function of this IB and IE? And you will get the answer for this question. Please change the rotation of this. Change the rotation of this. You will design one important question. So that is the first assignment for you. Then everyone try to solve this, and if you want the PDF, then join my Telegram channel. Then this is the right similar type of question. If you are changing the orientation, you will get this type of diagram current. If suppose current I am giving that is also wrong, then you will get the right answer. What is the right one? What is the right one? This is the assignment number 2. Now common sense, both the answers are wrong, then what is the correct one? This is again third one. This is a very important question. This is in instrumentation branch, my dear, and this type of questions we are expecting in electronics branch. That transistor is in what? Common collector configuration. Common collector means, and that's why it is called what? That's why it is called emitter follower voltage regulator. Emitter follower voltage. Why this much information is needed? Because MSQ, it is in pattern, multiple select question. They will give you the same question and they will ask what is the power dissipation, first option. Second option, it is also called emitter follower voltage regulator. It is in common base configuration, it is in common emitter configuration, it is in common collector configuration. This type of options we may expect. Then you have to get each and everything about the standard diagram. I think that concept is clear. Okay then. Thank you for attending the session. Join my Telegram channel, that is Electronics by Sanjay Rathi. If you want the PDF, you are on Byjus exam prep, the most comprehensive app for all exams. Join, subscribe our channel, like the session and share the link of this session. Okay. 1 minute. Okay then. Thank you and good luck for all coming exams. Thank you very much.